In this lecture, I'm going to discuss uh, radioactivity. Radioactivity. So before going to discuss radioactivity, it is important to have a brief understanding of what atom is and what a nuclear is. Uh, Nucleus of the atom is. So I had already discussed all these what is nucleus and what is an atom, how the constituents of the atoms, which are nucleons, protons, and neutrons, are held together, and why something is stable, some nucleus is stable, some is unstable. I had already discussed in our previous lecture, which is understanding the NZ curve. But let me discuss very briefly here what is an atom, what is a stable, and what is unstable system. So we all know that we have an atom. This is my atom, uh, in which I have a nucleus, in which I have protons sitting inside the nucleus, protons and neutrons inside the nucleus. So inside the nucleus, I have protons and neutrons are sitting inside the nucleus, and then around the nucleus, I have electrons. I have electrons. Mm, I have electrons revolving around the system, the nucleus. Okay, electrons revolving around the nucleus. So uh, these are my electrons minus, and say this is these are protons which have a plus E plus charge, and uh, these are red one is neutrons which has no charge, and this all together, this area, this space is known as the nucleus of an atom. Nucleus of an atom. Okay, so and we know that nucleons are basically protons and neutrons. So uh, this is how we look into an atom, in which you have a nucleus, and electrons are revolving around this. And the protons are responsible for holding these electrons revolving around in a certain orbit around the nucleus. So the important points which we have to remember, that uh, a strong nuclear force A strong nuclear force holds the positive, holds the positive, positively charged protons and neutrons and neutral neutrons together and make the nucleus what we call stable. So, uh, what is a stable nucleus means? So, what is a stable nucleus means? So, a stable nucleus is the one in which the nuclear force is strong enough to hold the nucleons all together permanently. So, uh, a stable nucleus is a nucleus uh, in which the nuclear force is strong enough to hold the nucleons together permanently. When I say to hold together nucleons permanently, that means this is stable. Because and why the nuclear force has to be stronger, because we know that there are Coulomb force is there because of the presence of the positively charged protons. So if the nuclear force is we know that inside the nucleus we have a Coulomb force also, Coulomb force, which is repulsive as nature, which is repulsive. And then what we have is nuclear force, which is attractive. So if this force is strong enough to overcome the Coulomb force which is acting between the protons, then the nucleons of the system are held together permanently, and this is what we know as an stable nucleus. But not all nuclei are stable. But not all nuclei are stable. So unstable nuclei. So what is an unstable nuclei? So unstable nuclei have either too many protons, too many protons, or too many neutrons, which actually upsetting the strong nuclear force, which actually upsetting the nuclear force, which is holding them together, and that's why they are unstable. So unstable nuclei. So in that scenario, What unstable nuclei do, unstable nuclei try to balance themselves. Unstable nuclei try to balance themselves uh, by giving off the excess protons and neutrons, and this is called radioactive decay. This is called radioactive decay. So we can define radioactivity very safely now as that which is in case of the unstable nuclei. uh, okay let me define the radioactivity as it is a process of the self-destructing, the self disintegration, a spontaneous activity, a spontaneous activity in the form of radiations by some unstable nuclei, which is called natural radioactivity. So this is how we can define the radioactivity, that it's a self-integration process in which a spontaneous which is a spontaneous activity in which radiations are coming out from some unstable nuclei, and this is called the natural radioactivity. So this radioactivity uh, have been discovered the radioactivity was discovered by uh, the scientist French scientist named A.H. Becquerel in around is 1896. So this the phenomena of radioactivity, which is a self-disintegrating process, which is also a spontaneous activity, which is in the form of the emission of radiation by some unstable nuclei. So this phenomena was first discovered by this Becquerel in 1986. So radioactivity were classified into three types, which were according to their penetrating capacity. So uh, radioactivity were classified into three types according to their penetrating capacity. So the radiation which were coming out of radioactive material uh, was try to see that have been trying to see that what is their property and what is their charge. So property were these radiations were classified. Three type of radiation were coming out of a radioactive material, and these were classified firstly based on their penetrating capacity. As you can see that we have a cardboard here and aluminum sheet and the lead sheet. So the classification where the first was is the alpha particle, second one is the beta particle, and the third one was the gamma particle, the gamma particles which were coming out of a system. So you can see that this is alpha, this is beta, and this is gamma. This is alpha, this is beta, and this is gamma. So the alpha particle has the least penetrating power, because you can see that the alpha particle is going here and then it gets absorbed into the cardboard, but the beta particle is not getting absorbed in the cardboard and is going to the aluminum sheet, till aluminum sheet, and then it gets absorbed here. The most strongest penetrating power is for the gamma particle, which is not even absorbed by the thick lead sheet. So the more energetic is the gamma particle. Uh, the less energetic is the alpha particle, because the penetrating power of the gamma particle is the more, as in case of uh, as compared to uh, the alpha and beta particle. So we can write it here as a point that the alpha particle has least penetrating power, beta particle have more particles, have more penetrating power than alpha particle, and this gamma particles have most penetrating power than alpha or beta particles. So the first categorization is that alpha, beta, and gamma particles are, out of which the more energetic is the gamma particle as compared to the alpha and beta. The second one is on the basis of that a strong magnetic field is applied. So you can see that in this figure, a strong magnetic field is applied, and the direction of the magnetic field is directly perpendicular, and which is going into the page, which is going into the page. Okay, so this magnetic field is applied, and this is a system in which we have a sample, radioactive sample, out of which these three particles, alpha, beta, and gamma, are coming out, and then a strong magnetic field is applied perpendicular to the surface of this page, which is going inside. Then this has been found that the alpha particle is, when come out of the system, it basically deflected to the left side, and the beta particle is reflected to the right side, and then the gamma is going undeflected. So on this basis, it has been assigned that this alpha particle and beta particle are the charged one, because they are being deflected, are charged particles, charged particles, and the gamma is neutral because is not being deflected in a magnetic field. So this was the property in which And surely that alpha and beta has opposite charges because they are being deflected in the opposite direction of the magnetic field. So based on these two experiments, that is the penetrating power and the deflecting the deflection in the strong magnetic field, perpendicular strong magnetic field, the radiation or the particles which were coming out from the system, a radioactive substance, were classified as the alpha particle, beta particle, and the gamma particle. So, but the next question remains that uh, how do we know that if an atom is stable or not? So, how do we know that a nuclei uh, is stable or unstable? This we can done, but if the when I have a nuclei, I will go to my NZ curve as I have already discussed in my lectures. You can go for my lecture on NZ3 NZ curve. This is my NZ curve. So by looking the position of the nuclei on the NZ curve. So as I told you that this is my n equal to z curve, all the nuclei which lie on this n is equal to z curve are going to have equal number of neutrons and protons. If any nuclei are lying on this n is equal to z curve, this is going to be stable. But the nature has found that this is this red curve is my line of stability, line of stability. So the combination of neutrons and proton, the most suitable combination of neutron and proton, which nature has chosen to be a stable combination, and they all lie on the line of stability. So those nuclei which lie on the line of stability are going to be most stable among its isotopes. So if I, as I have told that, if I draw a line and then on this line, like this nuclei, like this nuclei, all those nuclei which will lie on this line which will cross this line of stability. So these nuclei are the isotopes of the same nuclei. Okay, so among those isotopes, this one which is lying on the line of stability is going to be the most stable one, and all those isotopes or nuclei which are lying both side of this line of stability, either on the this side, on the right side or the left side, they are going to have instability. They are not unstable. So all these nuclei are going to decay and do the radioactivity. And we know that this line is known as the proton drip line, which I had already discussed. And this one is the neutron drip line. So all these about the drip line I had discussed in NZ curve lecture. And then so those nuclei which are on the right side of this line of stability, like these yellow ones, they are all known as the beta plus emitters. So why they are beta plus emitters, and all those nuclei which are lying on the left side of the line of stability, like these green one, they are known as the beta minus emitters. So at radioisotopes, isotopes, when I'm saying there's all these isotopes, and among these, this is the most stable one which is lying on the line of stability. So a radioisotope which is lying on the left side has too many neutrons, because you can see this line of stability, this line of stability is shifted towards the more neutron numbers. So basically we had discussed already that a system has to be stable. We need to have more number of neutron than as compared to the number of protons. So all these nuclei which are lying on the left side of this, they are having a more number of neutrons. So the nuclei which are on the left side had more number of neutrons, and therefore they're likely to decay through the beta minus emission. And you know that beta minus emission is nothing but a neutron is going to a proton plus electron plus an antineutrino. And similarly, all those systems which are lying on the right side of the line of stability, like these yellow ones, they are having a rich in a number of protons, so they are going to do a beta plus emission, in which a proton will becomes a neutron. This is having zero charge and plus charge. This plus charge, zero charge, and positron and a neutrino will come out. So I'll discuss on the next slide about beta minus and beta plus emission on the detail. And the rest is if a system is very high number of nucleon. So if I keep on increasing the neutron number and the proton number for a system, like if I have A greater than 200 or like Z greater than 82, uh, like if I draw a line, so if I Z greater than 82 or 83, so either this side or this side of line, this is those nuclei are going to be very large. Okay, so in such cases these nuclei are going to do an alpha decay, in which a system goes to an alpha decay, A minus 4, Z minus 2, and then we have 4 helium 12. So all these we will discuss in the next slide. So how do we know that? So those nuclei which are not lying either n is equal to z or on the line of stability, and they are down the line of stability, or the left side or the right side, uh, in between, within the proton or neutron drip line, they are all unstable, and they're going to they are the possible candidate of the radioactivity. Now, this picture shows the 5 ways in which an unstable nucleus can decay, and together with the reason for their instability and the finest nucleus, the process of decay, and the original nucleus. And I'll give you the examples of the nuclear transformation that accompany the various decays which are given here. So I'll first consider the beta plus and beta minus decay, which I had already discussed in the previous slide. That Let me say that this is first is the beta decay. Let me first is like beta decay. This is my beta decay. So beta decay is this beta decay is beta minus decay, in which you can see that I have a nucleus. This is my nucleus, and what is happening? The emission of an electron by neutron in nucleus changes the neutrons to a proton. So what happened that you can see that one of my neutron here, this is one of my neutron. You can see the gray one is neutron and the red one is proton, charge 0, and the proton has a plus E charge, and this black dot is an electron, and this circle is a positron. The positron is an antiparticle of electron. So here we can see that a neutron of the nucleus, my original nucleus, this is here, this is my neutron, and it is getting transformed into a proton. Okay, and then this one is the electron is getting out in that process. So this nucleus, which was original, in which one you can see one neutron is getting transformed into a one proton. So the earlier, the original nucleus having 1, 2, 3, 4, 5, 6, 7, 8, 8 protons, and then 1, 2, 3, 4, 5, 6, 7, 8, 8 neutrons. Now it becomes 1, 2, 3, 4, 5, 6, 7, 7 neutrons, and 1 2 3 4 5 6 7 8 9, 9 proton and 7 neutron. Okay, so but the a number remains the same, and the reason is given as because the nucleus has too many neutrons relative to the number of protons. If the number of neutrons are more in a given nucleus, then it certainly goes to through the beta minus decay. For example, if we have uh, I can write it like this. This is my original nucleus, AXZ, in which is having a number of nucleons and Z number of protons. Then it goes to beta decay, and then what happens? A remains same, Z increase by number of 1. As you can see, it becomes from 8 to 9. Neutron number remains same, and then an electron comes out in this process. So example, I can write an example that 14 carbon 6. If I say 14 carbon 6, when it does a beta decay, it becomes 14 nitrogen 7, and electron comes out in this process. So a new proton number from 6 becomes 7 because one of the neutron becomes a proton, and this is how if the system has large number of neutron, it does a beta minus decay and becomes a neutron becomes a proton. The second one is positron emission. uh, this one is the second one. This is beta plus emitters. The reason for doing such nuclei beta plus emission that it may have a more number of protons, so it too many number of protons, so it can the proton can transform into a neutron, and then system try to becomes stable. So here you can see 3 6 7 8. Again we have 8 proton and 8 neutron, and now one of the proton, you can see if I tag, this is one of the proton which is here, becomes a neutron, and then a positron coming out, a positron coming out, E plus is coming out here, E minus, an electron was coming out in such process. So and this proton, if you consider here, this proton becomes neutron here. So now what I have, we have 7 proton and 9 neutrons. 1 2 3 4 5 6 7, 3 4 5 6 7 8 9, 9 proton. So in such cases what we have is, if I have Z proton and a number of neutron, it has a beta plus decay, and what happens, we have a, here the proton number is decreased by 1. This is how we write a beta plus, and here we have a positron. Okay, for example, we can have 64, we can have 64 copper, and which have 29 protons, and then it becomes 65, it becomes 64 nickel, 64 nickel, and proton number decreased by 1, so it becomes 28, and then we have a positron coming along with it. So all those nuclei which are lying left side of the line of stability, having more number of neutrons, they go to beta plus, beta minus emission, and all those nuclei which are going on the right side of the line of stability, which have a more number of protons, they are going to have beta plus emission. The, uh, and the next one is like the competition of this beta plus emission is the electron capture. You can see that this is electron capture experiment. What happening is in this, that we have 8 proton and 8 neutron. This is exactly what we have. Uh, um, a proton is becoming a neutron, like beta plus emission. So this is my proton is becoming a neutron here. And this is electron capture processes in which we have a nucleus. Let me tell you, we have a nucleus in uh, which have a proton and neutrons sitting inside the nucleus. And if my this is my nucleus, and then the electrons are revolving around this. So what happens? The electron which is on this the innermost, this is my electron, the electron in the innermost orbit is being captured by one of the proton, and then it becomes a neutron, and it gets out of the system. Okay, this is one process. So this electron capture, as you can see, capture of an electron by proton in a nucleus changes the proton to the nucleus, and then that is what the electron is being captured by a proton and the neutron, and becomes a neutron. So this is also when the system has too many protons related to the number of nucleons. As you can see, the same argument is there, because positron emission or the beta plus emission is actually competing with the electron capture. If I see in this I write like AXC. What happens? This proton captures an electron, and then it becomes a system. A proton becomes a neutron. So because this capture this, and this electron by capture by this proton, and this proton becomes a neutron. So proton less number of proton is there. Okay. So for example, I can write this is like 64, the same 29, and this capture an electron, and it becomes 6428 nickel. Okay. Then we have, if we have a very heavy system in which we have number of A greater than 200 or number of Z greater than 82 or 83, then those system does an alpha decay. This is my alpha decay process. What happens in this an alpha particle? What is an alpha particle? An alpha particle an alpha particle is basically, this is helium nucleus. This is helium nucleus, which have two protons and two neutrons. Okay, so this is my alpha particle which have two protons and two neutrons. And so one of the alpha particle, like of the system, it comes out of the system, and this, there is no alpha particle. So if we have eight protons and eight neutrons, and two proton and two neutrons of the system gets out of the system, and it becomes six proton and six neutron. So this happens because when the system is too large. When the system is too large, then the system is not going one by one. One neutron, one proton is going to one neutron, one neutron is going to one proton. And what it does, it actually combination of two proton and two neutron, which is basically the helium system. It's come out of the system, and the system tried to reduce its size. So such kind of decay, radioactive decay happens. Radioactivity happens in when the system is too large. We can write it like this: if we have A x z, and what happens is alpha decay. This A is because four nucleons are getting out of the system, so A is decreased by 4, and then Z, because 2 proton is there, Z is decreased by 2, and then what we have is a 4 helium particle is coming out. For example, we can write it like we have 238 uranium, 29 So it goes to 234 a minus 4, and this will be 20, this will be, okay, this is not 29, this has to be 8, this had to be 92, this has to be 92, and it becomes 90z minus 2, and this is particularly thorium, and we have 4 helium 2. Okay, and the last process of radioactivity is the gamma decay. I write it like gamma decay process. What happens in which nucleus have excess energy. So when the nucleus is like an excess energy or being given some excess energy, the nucleons become into excited state. I'm putting in a star because whenever I write excited state, the nucleus which has excess energy, it is customary or conventional to put a star. So this system has excess energy, and it is in order to lose energy, it decays via it releases energy, and the energy is being released by the emission of gamma rays, which is reduces energy of the nucleus, and the final nucleus remains same. All the A, Z, and N of the system remain same, but what happens if the system has excess energy and loses its excess energy by the emission of the gamma ray? And the reason why, because the nucleus has excess energy. So this is written as this my if this is my system. So this is an excited state, has an excess energy. So we put in a star that this is an excited state, and what happens in order to release this energy, it comes down, it releases this energy and becomes the same system. And what we have a gamma coming out of the system. For example, we have 87 38 strontium. This is going to have an excited state, and then it comes to 87 strontium, 38, and we have a gamma coming out of the system. So these are all five basic process, known process, uh, through which an unstable system goes to the towards the stability. So not all system are going to have this beta plus, beta minus, alpha or gamma. What happens if I have a larger system which has too many nucleons, then as I have told you, it goes to the alpha decay. Even going to the alpha decay, after doing alpha decay or several alpha decay, it, the final nucleon, the final nuclei is not stable. So what happens, as it is decreasing its size, it's moving towards the lighter system, and when it comes to the lighter system, it start to decay through either beta minus or beta plus or the electron capture. So the combination of several process is helping out a system which is unstable to come towards the line of stability or being uh, a stable system. So this is all about basic brief sketch of the radioactivity, that what is radioactivity, why a system is unstable, how a system is unstable, and through what processes the system can go towards the stability. Thank you.